Hello, let's look into today's Leetcode problem, which is valid arrangement of pairs. In this question, you are given with edges for a graph, and what you need to do is return a valid arrangement of the edges. And by valid arrangement, what they say is this condition, that is end of I minus 1 is equal to start of I. End is basically the first index for an element, and second element for second index for an element, and start is the first index for an element. So this is how our output should look like. For ith index, the end of I minus 1, that is 9, should be equal to start of I, that is 9 here as well. Similarly, you can take it for any of the indices, and it will follow the same order. So if anyone came across Euler path or Euler circuit for a graph through that concept, then they should be doing it the right way. But for those who might not know what Euler path actually is, let me take an example and give a little bit of explanation. So I've taken one of the example from Leetcode and pasted it. So this is how the graph looks like for one of the inputs. So for such paths, for such graph, it's mentioned that there should always be a path. Uh, by path, what I mean is all of the edges for that graph should be visited once. So the first condition for a Euler path is all edges should be visited and only once. That is our only criterion for Euler path. So in that question, they've already mentioned that the inputs are generated in such a way that there will always be a valid arrangement of pairs, which means you will always find an answer. You will always find a Euler path for the inputs that's being provided. There could be scenarios where you might get more than one Euler path. In that case, you can return any one Euler path. Okay, so let's try to understand what Euler path actually means. I've written down a simple documented explanation here, but when you look into this example, right, you might have figured it out. So these things are actually calculated based on in degrees and out degrees, the Euler path. So the conditions for Euler path to exist is once you calculate the in degree and out degree for all the nodes present there in that graph, you should find this. There should be at most one node which has out degree minus in degree is equal to 1, and at most one node which has in degree minus out degree set to 1. Apart from that, all other nodes should have equal in degree and out degree. That's the only criteria that you need to do for checking if a graph has Euler path or not. Okay. But one thing I'm stressing again and again, there should be at most one. There could always be scenario, uh, not always. There could also be scenario where you have a graph like this, and for this graph, you won't find these two conditions, that is out degree minus in degree set to 1. But this condition is met. So for such graphs, Euler path will definitely exist, and you can start from any node, you will be able to find Euler path. Let's say you start with 1, 1 goes visits 2, 2 goes visits 3. All these three nodes, all these edges are visited basically once. 3 visits 1. If you take 2, right, 2 will go visit 3, 3 will go visit 1, and 1 will again go visit 3. All of these edges are visited and only once. So if you have all the edges which has in degree set to out degree, both of them are equal, then you will call it Euler circuit. So if you find a Euler circuit, definitely Euler path will exist. Many Euler paths will exist. In fact, all of the nodes can be treated as starting nodes, and we can find Euler path. But if a graph doesn't have Euler circuit, right, then you will find at most one. And if it's guaranteed that the graph has Euler path, then you will find one node which has out degree minus in degree set to 1. That is a guaranteed thing. So that is what we will be using. So this question is basically kind of like topological sort. Let's do a topological sort for this graph, right? So the topological sort will be 9, 11, 4, 5, and 1. And that is our Euler path indeed. So we can say it's a special case for topological sort, but you need to find a starting node for such graphs. So for finding the starting node, we already have come across this condition. So let's try to look into our solution. And for topological sort, you can do it two way. You can apply DFS or else Kahn's algorithm for topological sort. But for topological sort, you must have the graph to be a directed acyclic graph, which is not here in this case. Let's say for this example at least. So you can't proceed with topological sort if you have it in mind. I actually did it through topological sort when I wasn't aware of Euler path, Euler circuits and all. But now that I got to know about Euler path, my way of thinking changed a little. Okay, so let's look into our solution. So we are only given with edges in the beginning. So what we need to do is form adjacency list. And here I have used unordered map, that is basically hash map for this example, this question, because the nodes that we are given with are not linear in nature. That is like any usual graph problem which has node starting from 0 to n. It doesn't follow this way. So we will have to store the adjacency list through map, hash map. So for this example, 11 we should have a vector as value and key should be integer, that is the node. For 11 we should have 9, and if anything, for 9 we should have 4, and similarly like that. This is how we try to form the adjacency list. And similarly, like I said, we don't have any linear ordering of nodes. We have used a unordered map for finding the in degree and out degree as well. We iterate through the edges. We try to make the adjacency list as well as out degree and in degree matrix. Then, like I said, there could be scenarios where a graph could be Euler circuit, or a graph can only have one Euler path. So for that, what we do is we try checking for out degree and in degree difference, and if it turns out to be 1, then we found a start node. And if you are unable to find a condition where out minus in is equal to 1, then of course the graph is basically Euler circuit, because they said that you will always find at least one valid pair. So it should be a Euler circuit. You can take any node to be a start point. So I have taken one of the nodes to be start point. Basically, I took the first element for NH and then performed DFS on that. So how is DFS helping us here? So like in usual topological sort, let's say after I find the initial node, that is 11 for this example, I do DFS on 11, 11 calls 9, 9 calls 4, 4 calls 5, and 5 calls 1. And while backtracking, we simply store the pairs. So by pairs, what I mean is, um, okay, let me check once. Okay, so parent and then the neighbor. So one doesn't have any neighbor, so it backtracks, and 5 will be the parent that calls the neighbor, right? So parent and neighbor, 5, 1, then 4, 5 will be one scenario, then 9, 4 will be one scenario, and then 11, 9 will be our scenario. So while backtracking, I simply store the node and its neighbor. That's what I have written here. And this is our answer actually. If we simply reverse the stack and return it, it will get accepted. So what I did is I created an extra vector for that, because we should return our return type should be vector of int. So I've created a result, and on that stack I empty the stack, and while emptying it I store the elements back in the result array, and I simply return that result array. That's it. That's all how the question looks like. But one thing that everyone should notice here is we are not performing the traditional DFS that we used to do for graphs. That is, keeping track of visited array and then doing the DFS. Because it won't work for a few of our scenarios here. Let's actually take one of the examples for better clarity. And I'll explain you the through the code as well on what I did here. I actually did do DFS like we usually do, and it didn't work out for this example. Let's try looking into this example in deep. Okay. Okay. So one has edge towards 2, one has edge towards 3, and 2 has edge towards 1. And for this graph, 1 should be our start node because out degree is 2 and in degree is 1. So 2 minus 1 will give us 1. So let's try doing DFS for 1, right? Before that, let me form adjacency list for this. 2 will have an edge over 1. So once we start from 1, right? We do DFS on 1. 1 will try to iterate through and do DFS for its neighbor. But once we visit the neighbor, we visit the node, we mark it as visited, and DFS of 2 will be performed. And for 2, it it has only one neighbor, but it's already visited, so nothing happens. So while backtracking, 2 and 1 will get stored in the stack first. Then what happens is 1 will go call 3. So 3 doesn't have any neighbor in the adjacency list. We don't have any adjacency list for that. So 1 and 3 will be our next element. While backtracking, we will be pushing that. And ultimately, after the iteration ends, we will have 1 and 2. That's it. So how will our okay, it should be here. How will our resultant matrix look like? So it will be 1 2 1 3 and then 2 1 if I'm not wrong. Yeah. So this is how it looks like, but you can see that we are not having a Euler path here. 1 goes to 3 and then 1 1 goes to 2 and then 1 goes to 3 and then 2 goes to 1. Here the start node, end node, they are not matching, so it's not a actual DFS styles that we do here. Here what happens is 1 calls 2, 2 calls 1, and 1 is already visited, so there is an abrupt stop. And then again we are trying to continue iterating through one the neighbor of 1 and do DFS for 3. So because of this abrupt stop, we are unable to maintain the flow of DFS here, because of which we are not getting a right answer. That's the reason this is the DFS that we do here. So in this DFS, we are not abruptly stopped. So what we are doing is, instead of keeping a visited array like we used to keep it here, I simply pop out the index. So if you pop out the index from adjacency list, then obviously it won't get visited again, right? So once you pop it out, you do traversal on that, and while backtracking, you simply append it to the stack. This is how this DFS works. Let me walk you through an example here for better clarity as well. So initially, what happens is DFS of 1 will be called here. Let's write that down. So we are popping 3 from back, that is pop back. We do DFS on 3. Okay, fine. 3 doesn't have any neighbor. So while backtracking, we simply store 1 comma 3. That is what I have written here. Node and its neighbor. Node basically is our parent node. Okay. The next thing that we do is pop out 2. After popping out 2, I do DFS on 2. and DFS of 2 calls DFS of 1, and DFS of 1 doesn't have any neighbor, so 2 and 1 will be here, and in the end 1 and 2 will be stored in the stack. So how does the stack look like now? 1 2, 2 1, and 1 3. So it's a very elegant flow here, right? 1 calls 2, 2 calls 1, and here instead of abruptly stopping, instead of continuing the for loop after a stop, 1 directly calls 3, and then you do magical backtracking, and you get the answer. That's the reason this is the proper DFS that we do here. So if we don't have an adjacency list for that node empty, we perform this, and in the end, while popping, we push it in the result, and we return it. That's it. Simple as that. But two things that we have learned here newly is Euler path or Euler circuit, and the way we traverse here. So that's the beauty of this problem. And yeah, that's pretty much it. I covered whatever I wanted to say, and thanks for watching.